Metempsychosis, the doctrine of the transmigration or reincorporation of souls. See, transmigration. That's going to be my next entry. After my rain video, I had to follow up with meteorology. And it's funny how sometimes you've got to wait till the end for the good stuff. So if you haven't listened to my rain video, check it out, because at the end is when, wow, it's a long segment, At the end of the rain video, it talked about weather modification and that I should look up meteorology. So that is where I am now. I'm on page 5693. I am in volume 16, meteorology or aerology. The scientific study of the Earth's atmosphere and the phenomena of temperature, humidity, air pressure, and air movement, which produce varying climates and weather conditions. The study of average weather conditions in different localities over extended periods of time is often regarded as a separate science, that of climatology. The preparation of weather maps from meteorological data and the making of weather forecasts from such maps is called synoptic meteorology. Historical. Men have observed the changes of weather since ancient times and have compiled a number of rule of thumb observations, usually having to do with the appearance of the sky, for predicting storms or fair weather. The basis of scientific meteorology, however, is thermodynamics. And until the development of that science in the 19th century, meteorology made little progress. Exact observations are also of the greatest importance in meteorology, and the advance of the science has been furthered by the invention of suitable instruments for observation and by the organization of networks of observers to gather weather data. Weather records for individual localities were made as early as the 14th century, but not until the 17th century were any systematic observations made over extended areas. Slowness of communications also hampered the development of weather forecasting, and it was not until the invention of the telegraph in the middle of the 19th century that weather data from an entire country could be transmitted to a central point and correlated for the making of a forecast. One of the first scientific meteorologists was the German physicist Hermann Ludwig von Helmholtz, 1821 through 94. Who in 1888 described the general mechanism of the Earth's atmospheric circulation. He also recognized the existence of masses of air of different temperatures and humidity, and of surfaces of discontinuity now called fronts, where such masses meet. The modern science of meteorology, however, was not developed until the time of World War I, when a number of Norwegian meteorologists led by Wilhelm Bjerknes, 1862 to 1951, made intensive studies of the nature of fronts and discovered the mechanism by which interacting air masses generate the cyclones, which are the typical storms of the northern hemisphere. Later meteorological work was aided by the invention of apparatus such as the radiosonde described below, which made possible the investigation of atmospheric conditions at extremely high altitudes. Meteorological instruments. In order to obtain a clear picture of atmospheric conditions, a meteorologist must correlate many facts. The most important of these are air pressure, temperature, humidity, wind direction, and speed, the number and height of clouds, visibility and precipitation, the amount of rain or snow that has fallen. These observations are made at ground level, and usually a number of supplementary observations are made for the upper air. The standard instrument for measurement of air pressure is the mercury barometer, C barometer, which is more accurate than the aneroid. The latter type, however, is often used in a recording form called a barograph to show the trend of pressure over a period of time. All barometer readings used in meteorological work are corrected for variations due to temperature and to the height of the station, so that pressures from different stations may be directly compared. For the observation of temperature, many different types of thermometer are employed. One special type is the maximum minimum thermometer, which is arranged to record the highest and lowest temperatures occurring since the last observation. These thermometers usually have two separate columns, one of mercury and one of alcohol. The bore of the maximum thermometer is so arranged that the mercury column breaks whenever the temperature begins to fall, leaving a small amount of mercury to mark the highest temperature. In the minimum thermometer, a small metal index is placed on the alcohol column and sinks as the alcohol sinks with a drop in temperature. If a rise in temperature occurs, the alcohol column cannot raise the index and it remains at the point of the lowest temperature. Several instruments are used to find the relative humidity or the amount of water vapor present in the air. The most common is the psychrometer, which consists of an ordinary thermometer and a thermometer in which the bulb is covered by a cloth sleeve which can be dampened. Another instrument used to measure humidity is the hair hygrometer, consisting of a stretched human hair connected through levers to an indicating arm. See hygrometer. The most common instrument for measuring the direction of the wind is the ordinary weather vane, with a broad tail which keeps it pointing into the wind and which is observed directly. Sometimes, however, the vane is connected to a series of electric switches which light small bulbs at the observer's station to show the wind direction. Wind speed is measured by the means of a cup anemometer, an instrument consisting of 3 or 4 cups mounted about a vertical axis. The anemometer spins faster as the speed of the wind increases, and some form of device for counting its revolutions is used to gauge the wind speed. The wind close to the earth is slowed by trees and buildings and by friction with the ground. To determine the steadier winds aloft, meteorological observers release small pilot balloons which rise at a steady, known rate of speed. By determining the position of these balloons by means of the theodolite, the watcher can calculate the speed and direction of winds at various levels until the balloon passes out of sight. In case the sky is overcast with clouds, the time it takes the balloon to reach the clouds indicates how high they are above the ground surface. For other upper air measurements, 2 types of instrument are generally employed: the meteorograph and the radiosonde or radiometeorograph. The meteorograph is a lightweight instrument containing a cylindrical drum turned by clockwork. 3 pens trace on the surface of this drum lines indicating the temperature, pressure, and humidity. A metallic thermometer, an aneroid cell, and a stretched hair respectively actuate the pens. The instrument, that's not very scientific, is it? We could do that. Actuate the pens. The instrument is sent aloft, attached to a balloon, and then recovered after the balloon burst at a high altitude. Sometimes meteorographs are also sent aloft by airplane or kite. The disadvantage of the meteorograph is that its records are not instantly available. This difficulty is overcome by the radiosonde, which is a lightweight radio transmitter arranged to send coded signals from instruments measuring pressure, temperature, and humidity. When attached to a balloon, the radiosonde sends out a series of such signals, giving an instantaneous record of conditions at various altitudes. Precipitation is measured by rain gauges and snow gauges. The former consists of an upright cylinder calibrated in inches. The latter is also a cylinder which is thrust into the snow. The core of snow thus collected is melted and then measured to obtain the equivalent precipitation of rain. The thickness of a snowfall in terms of snow is measured with an ordinary rule. Circulation of the atmosphere. The basis of modern meteorology is the recognition of the broad general patterns of circulation in the atmosphere caused by 3 factors: the warming effect of the sun, the rotation of the earth, and the friction between the atmosphere and the rotating earth. If all portions of the Earth's surface received the same amount of solar radiation, and the Earth did not rotate, the only motion in the atmosphere would be in the form of convection currents, see heat, as air warmed by the Earth rose, and colder air sank. However, the equatorial and tropical regions of the Earth receive more solar radiation than do the poles, and hence the air in the tropics is warmer than polar air. The warm equatorial air, being lighter, rises, and the colder polar air sinks. As a result, the air pressure at high altitudes in the equatorial region is greater than at the poles. At the surface of the Earth, the pressure is greater at the poles and smaller at the equator. Because air flows from regions of high pressure to regions of low pressure, there is a general drift of air in the upper part of the atmosphere from the equatorial regions to the poles, and at the same time cold polar air drifts toward the equator near the surface of the Earth. Air flowing poleward at a high altitude starting at the equator moves from west to east with approximately the same speed that the Earth moves from west to east at the equator. As the air progresses poleward, its west to east speed remains the same, but the speed of the Earth beneath it is less because the length of parallels of latitude on the surface of the Earth decreases with increased latitude. As a result, the north-moving current becomes a high-altitude westerly wind. In the lower atmosphere, the effect of rotation is exactly opposite. Air moving from the poles is moving from west to east less rapidly than the Earth and thus develops into an easterly wind. The effects of centrifugal force complicate the circulation pattern still more. In the northern hemisphere, for example, the upper air west winds moving faster than the Earth tend to move outward centrifugally and are forced southward, and the east winds on the surface are forced northward by their comparative lack of centrifugal force. As an air mass is moved southward by centrifugal influence, it tends to build up pressure ahead of it until the pressure is sufficient to stop the flow of air. And at the north, a similar pressure is built up by the air moving northward. In the northern hemisphere, therefore, an observer facing downwind always has an area of high pressure at the right and low pressure at the left. Thus, the circulation of wind about a low-pressure area is always counterclockwise or cyclonic, and the circulation about a high-pressure area is clockwise or anticyclonic. In the southern hemisphere, these directions are reversed. The combined effect of all these forces on air circulation can be summarized as follows. Ground air in the regions near the equator rises, drifts northward and southward, and becomes a westerly wind. As the air goes poleward, it loses some heat and therefore becomes heavier and sinks to ground level. This phenomena occurs at about 30 degrees latitude. Once the air has reached ground level, part goes north and part goes south. The portion moving toward the pole becomes a westerly ground wind, and the portion moving toward the equator becomes an easterly ground wind. The polar air moving toward the equator and becoming an easterly ground wind meets the westerly ground winds from the equator at a latitude of about 60 degrees. The warmer air is forced upward and tends to circulate back towards the equator. As a result of these movements and interactions, the circulation patterns in each hemisphere includes easterly ground winds from the equator to 30 degrees, prevailing westerly ground winds from 30 degrees to 60 degrees, and easterly ground winds from 60 degrees to the pole. The winds of the upper air are westerly from the equator to the pole. The polar front. The most important weather-producing area in the northern hemisphere is a belt about 60 degrees north, the so-called polar front, where polar air and equatorial air meet at ground level. The belt is characterized by alternating spells of wet and dry weather, as dry polar air and moist equatorial air alternate. The polar front is not regular but is broken up into waves by the action of centrifugal force on the moving air masses. This force results in the formation of cyclones as masses of polar air move south. Cyclonic winds veer from easterly to northerly, and as they move north, veer again anticyclonically, and then repeat the entire process. During the winter, the polar front region frequently covers the entire United States. In the summer, when the temperatures in the far north are not greatly different from those in the tropics, the front recedes. The waves formed on the polar front vary in length with the strength of the westerly winds south of the front. When these winds are very strong, the waves are comparatively few and far apart. When the winds are less strong, the waves are closer and a number of tongues of cold polar air push southward. While currents of warm air move north, the polar front is thus broken up into a series of fronts, each of which in general stretches from southwest to northeast. Along these major divisions of the front, smaller wave disturbances are formed. These are cyclonic in form and are the waves responsible for the changes in our weather. The general motion of these waves is from west to east. In a typical wave of this type, the crest of the wave, formed of warm southern air, replaces the cold air and pushes up over it, forming what is known as the warm front of the wave. Behind the warm front, in the trough of the wave to the southwest, cold polar air overtakes the warm air and moves under it like a wedge, lifting the warm air. This part of the wave, which is characterized by rain and squalls, is called the cold front. Because of the counterclockwise motion of the wave and the swifter motion of the cold air, the cold front finally overtakes the warm front, producing what is called an occluded front. The occluded front is more stable than the cold front, and the weather pattern tends to continue in a settled cyclonic pattern. In the summertime in the northern hemisphere, the general polar front pattern is similar, but as the variations in temperature are less extreme, larger and slower moving cyclonic patterns tend to develop. In the southern hemisphere, which has smaller continental masses, the polar front pattern is quite regular and there is less seasonal differences in the types of weather experienced. Jet stream. Within portions of the air masses in motion at altitudes from 10,000 to 50,000 feet above sea level are narrow bands of high-velocity winds called jet streams. At levels of 50,000 feet, such winds may attain a maximum speed of 250 miles per hour. A jet stream may encircle the world in a wave-like pattern, but frequently it is broken up into several discontinuous segments. Jet streams exert considerable influence on the weather. Weather forecasting. The basis of scientific weather forecasting is the collection of data from a large number of stations scattered over a wide area. This data enables the meteorologist to obtain an accurate picture of the composition and motion of the various air masses which will interact to produce specific future weather conditions at the point for which he is making his forecast. The general procedure of making a forecast involves first receiving and entering data from observers at the proper locations on a base map. By sketching in on the map isobars, lines joining localities having the same barometric pressures, the meteorologist can locate the areas of high and low pressure and can also determine the general position of the fronts between them. His information from individual stations as to the temperature, humidity, and presence or lack of precipitation gives him a clue as to the processes taking place in the atmosphere at those places. Separate maps are usually drawn to indicate the types of clouds at various altitudes and their motions, and the rate of change of pressure at the various stations. These charts usually suffice for the preparation of a 24-hour forecast. So many variables are involved in the preparation of weather forecast that complete accuracy is nearly impossible. Forecasts for small areas covering comparatively few hours can, however, usually be made with great accuracy. In recent years also, progress has been made in the development of techniques of long-range forecasting for periods of 5 days and even longer. A particular value of such forecasts is that they represent with fair accuracy the general tendency of the weather during such periods, enabling farmers and businessmen to foresee and prepare for rainy or dry spells. The method of weather forecasting through the use of giant electronic computers creates the possibility of making long-range predictions with accuracy. Machines used in experimental tests, 1954, were capable of performing in 1 hour all the calculations necessary for nationwide daily wind predictions. The chief weather forecasting agency in the United States is the U.S. Weather Bureau of the Department of Commerce, which maintains over 350 full-time offices. Weather maps are prepared 4 times daily for 14 different parts of the country, based on data collected from about 1,000 reporting stations. The Bureau also operates a number of special services which warn of hurricanes, cold waves, floods, and excessively dry weather in forest areas. Private weather forecasting services are also maintained by individual companies, particularly by airlines. These services prepare specialized forecasts to suit the particular needs of one industry or one locale. Commercial weather forecasting services also exist which sell specialized forecasts to industrial clients. Okay, and this is the one I was waiting for. Weather modification and control. In recent years, meteorologists have investigated the possibility of modifying the weather by seeding clouds with various substances. Considerable research was done on fog dispersal as a method of increasing visibility for aircraft, but the purpose of most experiments is the artificial production of precipitation. Scientific evaluation of the various techniques require controlled study to distinguish the amount of rain induced by artificial means from that which might have occurred naturally. This distinction is difficult to determine as the meteorological conditions essential for the artificial production of rain are similar to those leading to natural rainfall. Available evidence from experiments by both private and public agencies indicates that cloud seeding may alter the timing or the total amount of precipitation falling over limited areas if the meteorological conditions are favorable. For supercooled, below freezing clouds, the most effective seeding agent is dry ice. The method adopted by many commercial agencies of seeding such low temperature clouds with silver iodide particles was found to give poor results, especially when the particles are dispersed from ground generators instead of from aircraft. Warm cumulus clouds containing updrafts may be induced to release rain by fine water sprays or by seeding with salt particles. Despite the limitations thus far indicated by the results of cloud seeding experiments, attempts to effect weather control are considered inconclusive, and meteorologists recommend further experimentation in this field. Late in 1953, President Dwight D. Eisenhower established the Committee on Weather Control and Evaluation to make a study of cloud seeding experiments and, on the basis of its findings, to propose legislative recommendations for weather control projects. So there you go, meteorology. There are several pictures. Meteorology. Left. Sending a radiosonde aloft on a balloon. This instrument measures pressure, temperature, and humidity at high altitudes and sends radio signals, which are picked up by a receiver at left. Right, top, barograph, for recording air pressure. Right bottom, wind tower containing anemometers, storm indicator, and weather vane. And then here, top, meteor, oh, this is meteor, but I'll go ahead and include it. Okay. Top, meteor falling to the earth in straight path produces contact flash and a deep crater. Bottom, meteor falling in a zigzag path produces explosion and shallow crater. I'll go ahead and include that. And then on the front, let's see if I've ever shown this. Sure. Yeah, I have. Okay, I hope that you have enjoyed this extended view from the past of my Funk and Wagnall wealth of information, and have a fabulous day. Please leave a comment. Let me know if there's something you want me to look up. My next entry will be transmigration. Hopefully it's a longer than a few lines. Sincerest Kimba.